Salutations. So we did homogeneous linear second order equations in the previous session, and now we're talking about the non-homogeneous. So what is now new is, so to remind you, this is how a second order linear looks like. Linear because there's, oh, again, I forgot my y here, because there is a linear in y prime and linear in y, and then there's a constant here, that's the forcing function. If this is non-zero, then we're dealing with a non-homogeneous case. Okay. Now, I'm going to, what in this section, again, we will do what I did in the previous one, is basically giving you general solutions, and then you have to figure out what the particular solution with the initial conditions looks like. So, again, the method of finding solutions is not yet, we're going to discuss that next. That's going to come in the next lectures. So now it's just basically setting up how do we, once you have, how do this all fit together? Okay, and moreover, you will see that solving non-homogeneous one will be even much harder in general. We'll discuss that also next time. But let's now look at just the general theory. So I remind you, so for the homogeneous one, if you have a homogeneous, what was there was we had this fundamental system of solutions. You know that it existed, and it were a fundamental system. It looks like there are many, no, it's just two. Y1 and Y2. Let me end here that we see what I'm, Y1 and Y2. And fundamental here means that Y1 over Y2 is not a constant. They're not proportional. One is not a constant multiple of the other. Okay? Then we know that the general homogeneous solution, so I'm going to write my H for homogeneous. The general homogeneous solution looks then as C1y1 plus C2y2, what we call a linear combination of these for that fundamental system. And so any homogeneous solution looks like that. So now, we're going to talk about, so this is homogeneous solution. Now we're going to apply this to the complementary homogeneous equation. We know this, we have seen this notion for first order, right? In first order was you just take away the forcing function, you make that equal to 0, and that's exactly what we do here. So the complementary homogeneous equation is the same left-hand side, but now in the right-hand side you put equal to 0. Okay? And so the first thing we have to do is to solve, and that's if you look at what we did for first order, that's exactly what we did for first order as well, right? And then we looked for the particular solution. Particular kind of means just one, right? Particular solution, which I'm gonna write yp. So we find some particular solution, and then what we said was that the general solution, so y, this is the general solution. How does it look like? And that's why I present. The textbook presents it a little bit differently when we talk about first order, but I did it in such a way that it now should be clear that it's exactly the same. Namely, we take a particular solution, yp, that was this one, right? So particular means a single one, right? No constant involved, just one solution, and you add the general homogeneous. So this is the general homogeneous. That will be the solution. So in other words, if we write it down, yp plus c1 times y1 plus c2 times y2. Okay, so this is how our solution will look like, and now we can, if we have an initial condition, we can find what the c1 and c2 are. Be careful, the initial condition will be on the non-homogeneous one, so you cannot determine c1 and c2 from the complementary homogeneous equation. That's too soon, right? We had the same issue when we were dealing with first order. We had to wait. We can only do initial conditions at the very end. So once we have this full form, we have the initial conditions, we can find y1 and y2. So here so what is new now is this little term basically that we have to add, that is this particular solution. And let's see this at work right away. So I'm going to take this equation here. Let's look at examples. So I'm going to use just a couple of examples. And so the first one I want to do is y prime plus y equals 1. And I'm going to give you our initial condition. Y0 is 2 and y prime 0 is 7. Okay. So step 1 is the complementary homogeneous. Okay, and that will be y double prime plus y equals 0. Now, we haven't really discussed how to solve this. So, I'm going to write here later on, from later, so this is the black, for now it's something that we don't know yet, but later we'll see that the solution of this particular one is, there are two solutions, sine of x and cosine of x. Now, I want you to put it in perspective that it's actually something that we already saw in the previous video. If you look at, go watch this video and look at, we were discussing at that time this a little bit more general second order linear equation. Y double prime plus omega square is y, and then we noticed that the two solutions were sine omega y, omega x, and y2 is cosine omega x. So what is happening here? Omega is 1. So in this case, this is the case, omega is 1. Now, we didn't explain where this one comes from, so we didn't explain where this comes from, but we'll do this very shortly in the next lecture. So again, we accept now that these are two solutions, and we know it's a fundamental system, because y1 over y2 is sine x over cosine x, which is tangent x, and is not constant. That's the only thing we have to exclude here. So they're really different. Okay, so this means that the homogeneous solution in general will be a linear combination. Let's write a's and b's now. Sine x plus b times cosine x. But now, so this is the complementary homogeneous, step 1. Sorry, I had that. Step 2 now is the particular solution. And that is, here we even have less methods, as I said, and for now I'm going to just give you this, I'm going to just give it to you. So again, later, we will see that y equals 1 is a solution. Now, once, of course, I give you this, you see it right away, right? If you plug this in here, let's think about it. Y double prime is then 0, 1 equals 1. Oh, yeah, right. So this is actually the particular solution is very simple. What does it mean? This is a solution, but this is not the only solution. And it's definitely not a solution satisfying these initial conditions, because then what would it be? That y would be 1 and y prime would be 0, right? But that's not the case. Okay. So what to do now? Well, we now put things together. So this is yp equals 1. So yp, be careful, yp equals 1. 1 is a constant function now, okay? So the function that is constantly 1, that's the particular solution. Okay, so we now step 3, putting together. So step 2, at the moment there's no work because I just gave it to you. But later on, of course, we're going to have to fill in the blanks here. When these boxes that say later here, let me mark them. So these boxes that say later, those are things that we're going to have to do later, right? And then that's how we will get these results. Okay, so, but now we can put it together. What's the general solution? You take the particular solution, 1, and add the general homogeneous solution, a sine x plus b cosine x. That's the part that I had found here. Okay, and then step 4. Well, okay, and then perhaps the same step. We now do the initial condition. So if x is 0, y was 1, and the derivative, no, y was 2, and the derivative was 7. Okay, so we plug these two in here, we get 2 equals 1 plus a times the sine of 0, I'll write it up, plus b times the cosine of 0. But of course, this is 0 and this is 1, so we get 2 is equal to 1 plus b, so we see that b is 1. Now, to find a, we're going to have to find the derivative of y. So we calculate y prime. We do this using the equation that we have. The derivative of 1 is 0. The derivative of a sine x is a cosine x. And that is minus b sine x. So if I plug in now these two, I see that 7 equals 0 plus a times cosine 0, that's 1, minus b times 0 is 0, right? So we see that a is 7. Okay, so conclusion, the solution to this differential equation with these initial conditions is the function y equals 1 plus 7 times cosine x plus cosine x. Okay, so that's how it works. Okay, let's do another example. Now I'm looking at this one here, y double prime minus 2y prime plus y equals minus 3 minus x plus x squared. Okay, and initial conditions, y of 0 is negative 2 and the derivative at 0 is 1. By the way, I perhaps should have mentioned that already in the previous video. You might say, can we see this? Can we do these direction fields? Well, unfortunately not. Direction fields only show you y prime. Y double prime is not a direction. Remember, y double prime measures kind of the concavity. That's not plotting, that doesn't give us anything. So it's first order we can visualize using direction fields. Second order we can no longer visualize, unfortunately. Okay, so that's why these things are much harder already, second order. And unfortunately, as I said, most in many sciences, that's what we get, second order differential equations. Okay, but going back to the issue at hand here, so step 1, the complementary one, the complementary homogeneous equation, that is y double prime minus 2y prime plus y equals 0, right? So we put this forcing function, we replace it by 0. Now, again, we have our box, later box. From later, we will see that the solutions, that there are two solutions. Y1 is ex, I think. Wait, let me see here. Yeah, ex, and y2 is xex. Okay, now, is this fundamental? Is this a fundamental system? Well, we have to look at y1 over y2, which is ex over xex. The ex is cancelled, but not the x. So this is not constant. So here, see, by the way, you see ex and xex. Well, xex is a multiple of ex, namely x times ex, but not a constant multiple. That's why they are not. That's why they are fundamental system. Again, I didn't use this terminology, but for those that know linear algebra, have taken linear algebra, what we are saying is that these two functions are linearly independent. So if you don't know what that is, I mean, the textbook also mentions it, but for us it just means this here, that the quotient is not constant. That's the only thing you should think of. But if you know linear algebra, then this is what this means. Okay, so that's it. There's nothing else to do here. We know, therefore, that the general homogeneous solution will look like AEX plus BXEX, a linear combination of EX and XEX. Okay, the particular solution. Step 2, the particular solution. Now, this time I'm not gonna give you the solution right away. I'm telling you the particular solution will be of the form okay, A and B, I used A and B now already. Yeah, I used A and B on above here, so, but I would like to use the same A and B here also. Okay, I'm going to use A and B, but it's not the A and B's there yet, because we're going to let them use them. So the particular solution is going to be of the form A plus BX plus CX squared. What am I saying? So, and again, why? See later. Again, this is something we're going to do later. We will better know why this is, but at the moment, I'm just telling you. A particular shouldn't be of this form, but A and B and C are still to be determined. And where does this come from? Just to not have it completely looking randomly to you. Notice that this is a polynomial of degree 2. And what I'm writing down, I'm saying the particular solution is going to be a polynomial of degree 2. Some polynomial of degree 2. No, not necessarily this one, be careful. It doesn't have to be this one, we'll see, it won't be that one. Okay, so how do we do this? So this is now what is called later on the method of indeterminate coefficients, is we have to determine A, B, and C. So to find A, B, and C, we plug in to the differential equation, which this one. We plug into, let me copy it. We plug into this differential equation here. Okay. Now, notice that plugging in means that we need to know what y prime is and y double prime is. So let's calculate. So I'm going to now drop the p particular, right? In calculations we drop this. So y, of course, is just a plus bx plus cx squared. What is y prime? Well, that is the derivative of that is b plus 2cx. You with me? And y double prime is 2c. So if I plug this in, I get, so I'm going to plug this in here, right? Let me move this a little bit. Okay, so I plug this in. I'll color code it so that you follow. This one, this will be 2c, then minus 2 times, and I'm going to plug in y prime, b plus 2cx, and then finally I'm going to plug in y in here, so plus a plus bx plus cx squared. And the first thing we do is, there are different ways of dealing with this, but in this particular case the easiest way is comparing coefficients, and I'll explain what this means. So we plug in to this equation and then compare coefficients. Then compare coefficients. I will explain what it is. Compare coefficients. What I mean to say is, well, this is the left-hand side, right? So the left-hand side, this is how the left-hand side looks like. Let's write it in terms of x's. So combine like terms. So but first we have to expand this a bit. So we have 2c minus 2b minus 4cx plus a plus bx plus cx squared. So I'm going to group the constant terms, 2c plus a, 2c, sorry, I forgot one, 2c minus 2b plus a, that's the constant term. Then the terms that have an x in it, we have a b and a minus 4c. Let me write this one this way. Okay, and then finally we have the cx squared. Okay, so this is the left-hand side. Now the right-hand side is the given f, the forcing function. This is our right-hand side. So it's minus 3 minus x. Let me write it a little bit. I'm going to, okay, no, let me do it already. So I'm going to write this polynomial a bit. I'm going to match it so that we align everything with the variables here, plus x squared. And what does now mean compare the coefficients? Well, let's look. What is the coefficient, the constant term? So this is the method of comparing coefficients. So what I'm now explaining is, let me compare coefficients. What does this mean? Well, let's look at the coefficient of the constant term. So we would have, this is the constant term of the left-hand side, this is the constant term of the right-hand side. So what we're saying is that they have to be equal. So we say that minus 3 is equal to 2c minus 2b plus a. Oh, well, 3 unknowns, one equation is not enough, but we have more, right? We also have this constant coefficient here of x must be the same as this coefficient, which is minus 1. So we also have that minus 1 is equal to b minus 4c. And then finally, and perhaps somehow you would like to have started with this one, because this is the easiest one, right? This is c equals 1. 1 equals c. So we know what c is, and then we can plug it therefore in there. And so we get this is b minus 4. And there we can solve for b. So we see that b is minus 1 plus 4 is 3. And now we can plug this in here. C was 1. So I'm plugging c in here and I'm plugging b in there, right? So I get 2 times 1 minus 2 times 3 plus a is minus 3. So what do we have? Minus 3 equals 2 minus 6 plus a. Bring everything to the other side. I get this is minus 4. Bring this to the other side. 4 minus 3 is a. So I see that a is 1. So a is 1, c is 1, and b was 3. So we find our particular solution is, it was of this particular form, a plus bx plus cx squared. Oh, you might have perhaps protested a little bit, why do you write in this form? Don't we set the c normally, and the a and the c are mixed here? We normally write this, I know. I'm sorry, yes. I didn't write it in the standard form that you used to with the a's and b's and c, but that's really not important here, right? You can name these variables whatever you want, and you can that's not important. Eventually you will find the same answer, namely the answer is 1, b, what was b? 3 plus 3x, and then c was 1 plus x squared. So that's your particular solution. So now step 3, we put in this together. We know that the general solution is this particular solution. So here's the formula. Let me highlight the formula where we're using this here. This is the formula that I'm now referring to, right? This here. The general solution is a particular solution plus the general homogeneous solution, and the general homogeneous solution is like this. So if you want, this is really the formula. Okay, write that out. So y is this particular solution that I just found, and then we had these two solutions that we knew was a fundamental system, namely ex and xex, and so we have to take an arbitrary linear combination, and here I'm going to using my a and b, but I've used them now, I can reuse them. Ax plus b x ex. So that is the general solution. Now we need to still know what a and b is, because that's where our initial conditions come in, and they were -2, and so y, if x is 0, then y was 2 and y prime was -1. No, 1. Oh no, it's the other way, -2 and 1, sorry. -2 and 1, I knew there was a minus somewhere. Okay, so let's plug this in. If you plug these two in, I get -2 is equal to 1, x's cancel, plus a e to the x, e to the 0 is 1, and b x ex is also 0. Oh, that's easy. So I find that a is -1. Now we need y prime. So I need to calculate y prime. This is always part of the calculation in initial conditions, right? And that is, we take derivatives, that is 3 plus 2x plus aex. Now be careful, we have a product here, so I'm going to have to do the product rule. B is just a constant, bx, derivative of bx is b, copy the second one, plus copy the first, and now take derivative of the second one. Okay, and okay, I plug in x is 0 here, so let's be a bit quick. X is 0, this goes, so this will be 0 and this will be 0, and so what we get is plus 1 equals 3 plus a to the e0, that is a, plus b also, and that last time was 0, but we know that a was -1, so this is 3 minus 1, I'm using that here now, plus b, and so I can solve for b, get, this is 2, and so 1 minus 2 is b, so I get that b is also -1. So conclusion, my solution was 1 plus 3x plus x squared minus ex minus xex. Let me see, is that the same thing that the textbook gives? No, what did I do wrong? Oh, of course, here, this is -3, right? Yeah, we have to, get a little bit late, a little bit tired. So, okay, sorry. So this is, therefore this b is also going to be wrong. So let's do the b correctly here also. So what's the b here? So a is -3, because this becomes a -1, right? So see, if you go too quick, you make mistakes. I should have done it little by -1, and then I would have figured it out. So now I plug in, 1 is 3 minus 3 plus b, and then I see that b is 1. So this would be minus 3ex plus xex. So that's the solution. Now this is just a little bit number crunching. This is not so important, right? Okay. Right. I'm not going to do more examples because it's kind of not really helping that much yet, because we don't have yet general methods to find solutions. So I'm going to finish with one more result, and this is called the principle of superposition. Superposition. So remember I said if you have a non-homogeneous equation, then the f is sometimes called a forcing function, because it's a force that acts upon this object that creates this, describes this motion. Now, sometimes you have different forces working on an object, and if you would combine all the forces, you get really very ugly. So you would like to do this, you would say, okay, if one force is working and then the other force is working, so perhaps somehow, how do I combine this? So I'm not going to talk about the mechanics of it or the physics of it. I'm going to talk about the mathematics of it. So suppose we have the following differential equation. And we have this forcing function f1. And then we have the same differential equation, but with a different forcing function f2. So be careful, right? So the homogeneous part is exactly the same. I'm just saying we have two different ones here. So okay, suppose that y1 is a particular solution here, and y2 is a particular solution there. Okay? Now let's think about what happens. What does that mean? If I put in y1 in this expression, I get f1. If I put in y2 in this expression, I get f2. What happens if I put in y1 plus y2 in the same expression? Well, because, and this is what linear means. If you put in y1 plus y2, this sum breaks up in a part with y1 and part with y2. Okay? What happens here? The same thing, because if I take derivative of y1 and y2, I get y1 prime and y2 prime. And the same for double derivative, y1 prime, y double prime. So what I'm saying is, if I plug this in here, let me write it up. So if you have y1 plus y2 double prime plus px y1 plus y2 prime plus qx y1 plus y2, we know that the first double prime gives me a y double prime. Okay. Now let's gather the terms that contain y prime. Contain y1 and its derivatives. So the next one, so the y1s I'm going to write. This is one y1, there's a y1 term here, and there's a y1 term there. Now, of course, this is y1 prime, right? So we get px y1 prime plus qx y1. And let's now do the same for the y2s. These are the y2s. And you get same expression, but now with y2. Okay? So if I plug in y1 plus y2 in this homogeneous part, then I get actually two parts. This one, let me use the colors. The red one comes from y1 and the green one comes from y2. But I said that if I plug in, so the red one, if I plug in y1, I get f1. So this is f1. And I also said that if I plug in y2 in here, I get f2. That's what it means to be a particular solution. So this means it's f2. Oh, green. This is f2. So what I get is that conclusion y1 plus y2 is a solution of the following equation: y double prime plus pxy prime plus qxy equals f1 plus f2, right? That's exactly what I get here, f1 plus f2. And this is exactly what I was saying. You have a force f1 and you have a force f2 that make the determined part of the movement, and the rest is the differential equation, of course. We'll see it later when we talk about mechanics, how these f's are actually really forcing functions or come from a certain force. And so what this says is, okay, if you have one force and you find a solution, you have for another force you find a solution, and now both forces all at once start to work, no problem, you add the solutions. So let's just to have one application of that. So suppose we have here we have x square y double prime plus 4xy prime plus 2y equals, and now I'm going to have two different forcing functions. The first one is 2x to the fourth, and the second one is x square, no, 2x to the fourth, and this is 4x squared. Okay. Right. So let me perhaps, let's try to find a solution. And again, the homogeneous one, let me tell you what the homogeneous one, because that one, no, I don't even want to solve the homogeneous one. I'm just talking about particular solutions, okay? So let's find a solution y1 for, this is my f1, for f1 equals to 2x to the fourth. Now, again, I'm not going to tell you why this is working. I'm saying I'm going to claim, so again, later, I'll put it again like later. Later we'll see that part of the theory tells us that a solution of this particular type of differential equation, it's still a linear one, although there's an x squared in front of y double prime, but we can divide it out, is of the form ax to the fourth. So there's just some multiple of x to the fourth, but which one there's only one a that works. So let's try to find what this a is. Later, so I'm saying that later we'll see that this is a particular solution. So the same way that we said here, a particular solution will be of the form this one, okay, but why, that we have not discussed yet. So now I'm saying the particular solution will be of this form, but why, we discussed it. But knowing that's of this form, let's find it. What we need to do, well, we need to plug it into this equation. So we have the equation, this is the equation that we're trying to solve, right? Let me write it one more time, in case it's not clear, that I'm now looking here at this equation. So I need, okay, y is a x to the fourth, y prime is 4ax cubed, and y double prime is 12ax squared. So I'm plugging this everything in, x squared times 12ax squared, I hope that you see where everything comes from, plus 4x, y prime is 4ax cubed, plus 2 times ax to the fourth, and there's 2x to the fourth. And you see what happens miraculously, all the powers are x to the fourth power. So let's write down what we have here. You have 12a plus 16a plus 2a, right? So this is 12a, we have 16, and you have 2a. All these are the powers of x to the fourth, and this is 2x to the fourth. Comparing coefficients, or cancelling x to the fourth if you want, this is even simpler, but it is really comparing coefficients, so I'm going to write it that way. It's simpler than the general case, but it is the same principle. Comparing coefficients, we see that 12a plus, okay, I can actually work this out. It is 30a, right? That 30a must be equal to 2, and so we see that a is equal to 1 over 15. Okay, so I find that my solution, y1, is 1 over 15 x to the fourth. Remember, I could yp here, but let me call it y1, because this was for f1. And for the other one, same principle. So for y2, so now f2, instead of 2x to the fourth, it was, what did I say it was? 4x squared. So for this one, we do the same thing. So we have done all the calculations, right? So no, we don't. So now I'm saying that y2 is of the form, not a fourth power, but a square. Again, y later. But if you know it's of this form, we can find it, because y is then ax squared, y prime is then 2ax, and y double prime Yeah, let me not write the 2's anymore, because that's getting annoying. So this is something we very often do. I've said this now many times, that during calculations I drop the subscripts, but once I put everything together, I have to make sure that there's so many different y's running around that I put the right ones together, right? Okay, so we plug this into this differential equation. This is x squared times y double prime, 2a, plus 4x times y prime, 2ax, plus 2y, so 2ax squared, and that is equal to, what was it? 4x squared. So again, we see that this is 2a, we have an 8a and a 2a, that is 12a, and everything is x squared equals 4x squared. So we see that 12a is 4, and that a is therefore 1/3. So we see that y2 is 1/3 x squared. Okay, so we found the particular solution. We didn't find the homogeneous one. I'm not going to even discuss them, but so superposition now tells me, the superposition principle, what does it say? Suppose we have this differential equation. Where is the differential equation? Sorry, I should perhaps copy it. Let me copy it here. This differential equation. Clicking on the wrong thing. Okay. Differential equation, this is the homogeneous part, equals now the sum of these two guys, f1 and f2. Remember, f1 was 2x to the fourth, and this was 4x squared. So 4x squared plus 2x to the fourth. So the solution, I should say a solution, not all the solutions, is therefore the sum of the two solutions that I found. That is 1/15 x to the fourth plus 1/3 x squared. So this is a solution. Now, of course, if there's an initial condition, this might not be the right one. And that's why we also need to know what homogeneous are. But that's for later again, solving these. I'm just want to show you the principle of how you put everything together. So what we have seen in the last, the two videos that we have seen so far on second order, the two things we have done is homogeneous. We know now that their fundamental system consisting of two different functions, different, right? Essentially different, really, not just a constant multiple of each other, and that everything else is in a combination of that, and then you have to find a particular solution in the non-homogeneous case and add that to the general solution, right? So the formula is really, it's adding really, and that is exactly where this terminology linear comes from. So this is basically the principle here that we are dealing with, is that we can add solutions, linear equation. Okay, and now what we will do for the rest of this chapter is then finding methods to actually do this and then implement this strategy. So this is basically a strategy, right? And so again, the homeworks will not be that much. You will always have to get the solution there, and since the textbook puts this already after 5.2, which I have not discussed yet, some of the homework problems I cannot assign yet. So I might assign homework problems to this topic after we do next session. Okay, so be aware that I'm reshuffling it a bit, but I find it more cohesive to put everything in together first and then look at the methods.